Good evening, good morning, good afternoon, good middle of the night. Whenever you're watching this, from wherever you're watching this, I greatly appreciate you taking a few minutes to hang out with me and talk about human interface device attacks. The title of my talk is Hidden Duckey, Deconstructed Payload. My name's Kevin Tyers. I'm a SANS Sec 504 instructor. In my day job, I work for a large financial institution. And I'm a huge Python and keyboard enthusiast, which kind of led me down the path of learning about hidden devices. Without further ado, let's go ahead and jump on in. So, what is a human interface device attack? Well, this is using some sort of device, in our case, maybe a evil USB rubber ducky, that you plug into a machine and it is able to act like it is a keyboard. Now, a lot of people think about like auto run attacks when it comes to plugging in USBs to machines, but that's not the only threat vector here. In fact, this one is arguably a little bit more dangerous because even if your company blocks, say, mass storage devices being attached to your machines, usually they don't block keyboards, which is good for someone like me, again, because I like custom keyboards, but it can be a little bit dangerous. So hid devices are able to be plugged into a machine and again run input as if it was a user sitting at the keyboard. And that means that anything you could do with a keyboard, which is quite a lot on almost every operating system, you can do and you can emulate with a hid attack device. So it's commonly USB, but it actually doesn't have to be. There are wireless versions of this using tools like Jacket, if you've ever heard of that. So here, right, we have our USB rubber ducky. We have an unlocked machine that someone's walked away from, which I suspect when we all start going back to the office, we're going to see people leaving their machines unlocked a little bit more because we've probably not been as diligent about it at home. And you're able to just run some commands. In this case, maybe I have something that's able to open up a terminal and curl down an evil executable. We run it, put it in the background, we kill the shell so there's no history, and now I have a piece of malware running on your network. Let's take a look at Duckey script just briefly so you can get an idea of some of the things you can do with hid attacks. So in this case, we're going to talk about Duckey script, and we'll come back to this example towards the end of the talk as we're demonstrating how to decode these Duckey scripts. So in this case, you can see we're typing GUI R, which brings up a run prompt. And we type in PowerShell, and we do a run as to try to run as administrator, and we do Alt Y to bypass the prompt that comes up. And then we're adding a user. In this case, we're adding Santa with the password of Klaus to the machine in question, and we're adding Santa to the administrators group because, let's be honest, he probably should have been there to begin with. Then we exit out of that, and lo and behold, we've been able to add a user to this machine. And I have a couple links here at the bottom that will get you more information and documentation about the Duckey script language that you can use to write these payloads. And the one thing about this is, again, it looks just like a keyboard input, but it's very, very fast. So if someone doesn't realize what's going on, they might plug this into their machine and, it would take less than 2 seconds for this attack to execute. So it can be very, very interesting and dangerous. All right, let's go ahead and talk about hid attack devices now, how we actually deliver these malicious payloads. So probably the most common hid attack device that people know about is the USB rubber ducky, but there's also things like bad USB, where you hide a little, machine inside of a USB cable that, just looks like a regular charging cable, but when you plug it in, your machine gets owned. There's also a whole beautiful world of custom keyboards that are actually able to do very similar functionality to this using a toolset called QMK. And I actually gave a talk, webcast on this for SANS earlier this year that you can check out at this link, or you can scan that QR code and that'll get you there. The talk is called Maniacal Keyboards. It's a really deep dive into some of the really interesting things you can do with mechanical keyboards for this area. So to actually load the payload onto a USB rubber ducky, it's pretty simple. You create a duckyscript.txt, which is just your Duckey script that you want to run, and then you can use, say, the Java encoder, which is sort of the default one that you would find on GitHub, and then you feed it in the Duckey code, and it spits out a inject.bin file, and that is a binary file that we're going to be looking at here for the second half of the talk. We move that onto a micro SD card, we put that micro SD card into our USB rubber ducky, and then we hack the planet. So let's get into how we actually decode those Duckey payloads. So if you found a USB rubber ducky device, either maybe the help desk turns it in or some helpful user, or you find a suspicious looking thumb drive on the ground and you open it and you see a micro SD card, let's see what these commands are. Alright, for this last part of the talk, I'm going to go ahead and kill the camera so we can focus on what's going on screen. So let's jump into decoding Duckey payloads, and I had an incredible amount of fun putting this section together, and I hope you have fun watching it. So let's say you have a USB rubber ducky that you find, and you can see my little video here on the left on how to actually get at that micro SD card if you've never done it before. You pop off the case, crack it open, and then in there you're going to see a little micro SD card. You pull that out and you can actually see mine's actually starting to get worn out. I've worn off the labeling on that. I've pulled it in and out so much. And then you can just plug it into a micro SD card reader. I plugged it into my Mac and it just popped up in Finder. Another really important thing to keep in mind is that if you're on Mac, right, you can just CD into volumes and then the USB device. Or if you're on Linux, right, it's just going to get mounted in the MNT directory off your root. So you can grab the inject.bin off of the device for later analysis. So let's look at how the Duckey script gets encoded into an inject.bin file and see if we can figure out kind of how it works. And here on our left side, we have the Duckey script of string A, which means all it's going to do, you're going to plug it in and it's going to type A. And then when we use XXD to look at the inject.bin, all you see is 0400. And already it looks a little bit weird to me, and I'll go into why that is in a moment. But let's add some more input into the Duckey script to see what happens when it comes out the other side. Well, in this case, I put ABC, which again, all it's going to do is you're going to plug the keyboard in, or the Duckey in, and type ABC. And the inject.bin has 040506. Now, I immediately knew that that was not the ASCII codes for A, B, and C. And in fact, I used Python to verify that here. I said, what is the, hex value of A? And it's, OX61, which is exactly what I expect. But OX61 is not 04. And it just so happens I've watched a lot of videos about USB devices and HID attacks. So I knew that what we were probably dealing with here was called scan codes. So I went onto the internet and I found a list of USB HID scan codes. And this fantastic GitHub here has all of the scan codes for USB. And as you can see at the bottom here, the key A scan code is 04, key B is 05, key C is 06, which matches what we saw in the previous slide. So now I want to figure out how modifiers work. So we kind of know what to look for and how to find these scan codes. Well, let's see what happens if I do a lowercase a and a capital A. Well, the inject.bin on the other side comes out as 0400, 0402. So knowing this, we can sort of infer that that 02 is probably important. So I looked for 02 in that HID scan code GitHub gist, and I found that that was a modifier for left shift. And I'll be honest, I didn't know this until I looked, but there's actually different scan codes for left and right modifier keys, which is pretty neat. So we can see that 0400 is an A with no shift. 0402 is an A with a shift. That's pretty neat. Let's say we wanted to look at what GUI R looks like to launch a run window in Windows. So here we do GUI R, and that gives us 1508. Now 15 is the scan code for R, and 08 we can see is L meta, or the meta key. This is also called the Windows key. It can be called the command key. I've heard it called super. There's all sorts of names for it, but ultimately it's our GUI key. In this case, we see 15 again as R and 08 is GUI. Combine those together, you have GUI R. It's pretty neat. If you had to do this by hand, you're starting to think that you might be able to do it. And let's actually look at an interesting example, because I was curious, how did Control-Alt-Delete work? Because I assumed that it was only these half words, or 2 bytes, that encoded all of the information. So how would we encode multiple modifiers? Well, if I put in Control-Alt-Delete into a Duckey script, I get out 4C05. Now 4C is delete, and 05, well, that doesn't appear in the modifiers. Interesting. But I noticed that if you add the Control and the Alt values together, you get 05. So that's pretty neat. So yeah, if you're holding down multiple modifiers, the scan code is just that second byte with the scan codes combined. So you might be looking at this and thinking, oh, this is cool and I can kind of understand it. And maybe you're the kind of person who's, base 64 decoded by hand once because you wanted to try it out. That's what I've done. But usually you want a tool that can do this for you, and you have a few options in this area. The first one is ducktoolkit.com. It's a pretty cool online resource where you can encode and decode Duckey scripts. I have found the encoding is just about perfect. I have found a couple instances where the decode doesn't work exactly as I'm expecting it, so that's just something to be aware of. DuckeyDecode.pl, and yes, that is a Perl script in 2021, is actually still pretty good. It actually comes with the GitHub where the USB Rubber Ducky code is hosted for Hack 5, so you definitely have that available. But I would like you to consider checking out a tool that I wrote called Mallard. I had been looking for a reason all year to write a USB Rubber Ducky decoder, and I got this strike of inspiration a few weeks ago when I was talking to Josh Wright that I was going to not only write something that decoded Duckey payloads, but it was also going to do some analysis. So we'll take a look at that in a second, and here's the link to that, or a QR code you can scan to go to my GitHub and get that tool. So let's step back. Let's look at that original Duckey script that we saw at the beginning, and look at the inject.bin that comes out of that. You can see here that 1508 that starts us off, that's that GUI-R we've already seen, and then we have this long string, and here I've highlighted Santa on the left in the Duckey script, and also where it exists in the inject.bin, and you can see, right, yeah, we see shifts, and we see, you know, that 0402, which we know is A, so we see that a couple times, and again, it's a cool party trick to be able to read the hex on this, but as these as these Duckey scripts get longer and longer, right, we're not going to want to have to look at the hex to figure out what they're doing. So let's use Mallard to look. So Mallard is a tool that I wrote in Python 3. It does absolutely require Python 3.7 because I use a few libraries that are new to that version of Python. We're on Python 3.10 right now, so it's not like it's scandalously new by any means. So if you're ever checking it out, go ahead and just run Python mallard-h. It'll give you the help output. And you can see here, right, we can feed it a particular file. By default, it just looks for inject.bin in your directory. If you don't want to do any analysis, you give it the -a. You can send the output to a file, you can send the analysis to a file, and you can even enable debugging if you're trying to add some functionality to it. So here's an example of running Mallard. So on my machine, I have an inject.bin just sitting in that directory, and I run Python 3 Mallard. And this is with no previous knowledge of what the Duckey script was. Like, obviously I knew what it was because I wrote it, but Mallard had no idea. It only had the inject.bin, and it came out just about perfect. I'm very proud of how this tool works. And again, that differentiator that you can see there at the bottom is I'm doing some analysis and commentary on the Duckey script that it was analyzed, right? So we see it run was opened, and you can see it says GUI-R, right? So it's possible Windows attack, PowerShell's invoked, a user was added, was added to the admins group. So I'm adding more and more of these detections and analyses to Mallard so that when you run a Duckey script or an inject.bin through it, that you don't have to think about it too much. It should just kind of give you an idea of what's going on. And then at the bottom, I just included a more complicated invocation of the tool where I have, Python Mallard, and then I give it a test file that's not inject.bin. I disable the analysis mode, and I turn on debugging. So thank you so much for taking some time to hang out with me and learn about hit attacks and learn about this tool Mallard that I released. Please check it out. Let me know what you think of it. My email is here. You can probably figure out what those special characters are supposed to be, but if not, look up those USB scan codes. Otherwise, enjoy Holiday Hack Challenge, enjoy KringleCon, enjoy 2022. If you see me teaching at a SANS event, please stop by and say hello, or if you take Sec 504 with me, I look forward to having you in class. Thank you.